Tonight the journey begins with a question that seems simple at first glance. What exists directly above the Sun? What lies directly below it? In the vastness of space, the answer is far stranger than most people imagine. There is no true up or down in the solar system. Yet when astronomers map the Sun's position through the galaxy, a hidden cosmic landscape emerges, one stretching across thousands of light years, filled with stars, dark clouds, and regions of space few people ever think about. Before settling in, take a moment to like this video and subscribe to the channel. These small actions help bring more calm journeys through space science and the universe. Now, as the solar system drifts silently around the Milky Way, the search begins. Above the Sun, below the Sun, and far beyond the familiar planets, a remarkable cosmic structure waits to be explored. The space immediately surrounding the solar system extends far beyond the influence of the Sun's visible light and heat, yet it is not empty. It is filled with a faint mixture of gas dust and charged particles that drift between stars. This region is part of the local interstellar environment, a broad and quiet structure within the Milky Way, where the density of matter is extremely low compared to conditions on Earth. Even so, it contains enough material to shape the boundaries of the solar system and influence how energy and particles travel through space. Within this region, the Sun moves through a structure often described as a local interstellar cloud. This cloud is a diffuse collection of hydrogen atoms, helium atoms, and microscopic dust grains. Hydrogen is the most abundant element, existing mostly in neutral form, meaning its atoms are not ionized. Helium is present in smaller quantities, also largely neutral. The density is extremely low, with only a few particles per cubic centimeter on average, yet across vast distances this sparse material becomes significant. The cloud is not uniform. It contains small variations in density and temperature, forming soft gradients rather than sharp boundaries. These variations arise from past supernova explosions, stellar winds from nearby stars, and the general motion of gas through the galaxy. The temperature of this interstellar gas is moderate by astrophysical standards, often reaching several thousand degrees in kinetic terms. However, because the density is so low, heat is not felt in the usual sense. Particles travel long distances between collisions, so energy is carried mainly through motion rather than conduction. The concept of temperature here reflects the average speed of particles rather than thermal sensation. Hydrogen atoms drift at speeds influenced by both the gravitational field of the galaxy and the magnetic structure of the interstellar medium. Magnetic fields thread through this region as well. These fields are weak compared to those found near planets or stars, yet they extend across light years and guide the motion of charged particles. The interstellar medium contains a small fraction of ionized gas where electrons are separated from nuclei. These charged particles respond to magnetic forces, creating slow, large-scale flows. Neutral atoms are less directly influenced, but can still interact through collisions and charge exchange processes, where an electron is transferred between particles, subtly altering their trajectories. Dust grains are another component of this environment. These are tiny solid particles composed of carbon-rich compounds, silicates, and ice-coated materials. They are much less abundant than gas atoms, but play an important role in absorbing and scattering starlight. When light from distant stars passes through the interstellar medium, dust can dim and redden it slightly. This effect allows astronomers to map the distribution of dust clouds and infer the structure of regions that cannot be seen directly. The dust also contributes to chemical processes, providing surfaces where simple molecules can form in the cold of space. The local interstellar environment is shaped by the history of stellar activity in the surrounding region of the galaxy. Ancient supernova explosions have pushed gas outward, creating cavities and shells of lower and higher density material. These structures overlap and blend, forming a patchwork of interstellar conditions. Some areas are warmer and more ionized, while others are cooler and more neutral. The solar system currently resides in a relatively low-density region that allows the heliosphere to expand outward without excessive external pressure. As the Sun travels through this environment, it carries with it a bubble of influence created by its own magnetic field and outflowing particles. This interaction defines the boundary between solar influence and interstellar space. The surrounding interstellar gas presses inward on this bubble, while the solar wind pushes outward. The balance between these forces determines the size and shape of the region dominated by the Sun. Even though the interstellar medium is thin, its pressure is sufficient to shape this boundary over time. Particles in the local interstellar environment also include cosmic rays, which are high-energy charged particles originating from distant astrophysical events. These particles move through space at nearly the speed of light and can penetrate deep into the solar system. Their presence adds another layer of complexity to the region, contributing to ionization processes and influencing the chemical state of interstellar gas. However, even cosmic rays are sparse enough that interactions remain infrequent on human timescales. The motion of the solar system through this environment is slow by cosmic standards. It takes tens of thousands of years to cross regions of differing density within the local interstellar cloud. Over time, this motion changes the conditions experienced at the edge of the solar system. The interstellar medium itself is also dynamic, with flows driven by galactic rotation and past stellar events. These flows create a gentle but continuous reshaping of the space between stars. Despite its thinness, the local interstellar environment represents a fundamental component of galactic structure. It is the medium through which all star systems move, and it provides the raw material from which new stars can eventually form. Its properties influence how radiation travels across space, how magnetic fields connect different regions, and how matter is distributed on large scales. In this sense, even the most distant and diffuse matter plays a quiet role in shaping the conditions surrounding the Sun. Beyond the local interstellar environment, the region surrounding the Sun transitions into a structure shaped primarily by solar influence, rather than external galactic material. This structure is not a solid boundary, but a gradual domain where the outward flow of particles from the Sun begins to dominate over incoming interstellar gas. It forms a vast protective region known as the heliosphere, extending far beyond the orbit of the outer planets. Within this region, conditions are controlled by solar activity magnetic fields and the continuous stream of charged particles emitted by the Sun. The heliosphere is created by the solar wind, a persistent outflow of plasma, composed mainly of protons, electrons, and small amounts of heavier ions. This plasma originates in the Sun's outer atmosphere and expands outward in all directions. As it travels through space, it carries with it the solar magnetic field, forming a vast spiral structure shaped by the rotation of the Sun. The flow is not uniform. It varies in speed, density, and energy depending on solar conditions. Faster streams emerge from coronal holes, while slower, denser flows originate from more active regions. As this solar wind expands outward, it gradually encounters resistance from the interstellar medium described in the previous region. The pressure from interstellar gas and magnetic fields counteracts the outward motion of solar particles. This interaction does not produce a sharp wall, but rather a broad region where forces balance in complex ways. The heliosphere exists as a dynamic response to this balance, adjusting its size and shape as solar output and interstellar conditions change over time. Inside the heliosphere, the environment is dominated by plasma behavior. Plasma is a state of matter where atoms are ionized, meaning electrons and nuclei exist separately. In this state, electric and magnetic forces become dominant over simple particle collisions. The solar wind plasma carries embedded magnetic fields that stretch and twist as the sun rotates. These magnetic structures influence how particles move, often guiding them along curved paths rather than straight lines. The outer edge of this solar influence is not fixed but varies depending on direction. In some regions, the solar wind travels farther before slowing, while in others it is compressed more quickly. This asymmetry arises from the motion of the solar system through the galaxy and from variations in the interstellar medium itself. The heliosphere is therefore not spherical, but more like an elongated bubble shaped by both internal pressure and external flow. Within this expanding region, particles from the Sun interact with remnants of interstellar atoms that manage to enter the heliosphere. These neutral atoms are not deflected by magnetic fields and can travel inward until they are ionized by solar radiation or by collisions with solar wind particles. Once ionized, they become part of the solar wind plasma and are carried outward again, creating a continuous exchange between solar and interstellar material. The heliosphere also acts as a filter for cosmic radiation. High-energy particles originating from distant supernovae and other energetic events are partially deflected or slowed by the solar magnetic field. While many still penetrate deep into the solar system, their intensity is reduced compared to interstellar space. This modulation changes over time, increasing when solar activity is strong and decreasing when it's weak. The structure of the heliosphere therefore plays a direct role in shaping the radiation environment throughout the solar system. Magnetic fields within this region are complex and constantly evolving. As the Sun rotates, its magnetic field lines are stretched into a spiral pattern known as the Parker spiral. This structure influences the motion of charged particles, creating regions of turbulence and organized flow. Small disturbances in the solar wind can grow into large-scale variations as they propagate outward. These variations include shocks, waves, and compressions that travel through the heliospheric plasma. The density of particles within the heliosphere is extremely low compared to planetary atmospheres, yet it is still sufficient to create measurable physical effects. Spacecraft traveling through this region detect variations in particle flux and magnetic field strength, revealing a structured and dynamic environment. Even in regions far from the Sun, the influence of solar activity remains detectable, showing how far the Sun's reach extends into space. At the outermost boundary of the heliosphere lies a region where the solar wind slows dramatically as it encounters interstellar pressure. This slowdown marks the beginning of a transitional zone where neither solar nor interstellar forces fully dominate. The flow becomes turbulent, compressed, and redirected. This region is not static but shifts over time as solar output changes and as the solar system moves through different parts of the galaxy. The heliosphere therefore represents a vast evolving interaction zone between a star and its galactic environment. It is not simply a shell, but a living structure shaped by continuous energy exchange. Within it, particles, fields, and radiation move in complex patterns that reflect both solar processes and external galactic conditions. It is in this region that the Sun's influence gradually gives way to the wider interstellar medium, completing the first large-scale transition from stellar environment to galactic space. The outermost reach of the solar influence continues into a region where the outward pressure of the solar wind begins to lose momentum, not because it stops emitting energy, but because the surrounding interstellar medium steadily resists its expansion. In this zone, the solar wind remains present as a continuous plasma flow, yet it becomes increasingly irregular, compressed, and turbulent. The structure is still part of the heliosphere, but it reflects a changing balance between outward solar forces and inward galactic pressure. Within this expanding flow, the solar wind carries charged particles that have travelled for billions of kilometres since leaving the Sun. These particles move through space as a collective plasma influenced by electromagnetic forces rather than simple ballistic motion. As the distance from the Sun increases, the density of this plasma decreases, but its interaction with interstellar material becomes more pronounced. The solar wind slows gradually, not in a single moment, but through a distributed process of energy exchange and compression. In this outer region, disturbances in the solar wind begin to accumulate. Variations in solar activity, such as changes in magnetic field strength or bursts of energetic particles, propagate outward and interact with earlier flows. These interactions create waves of compression and rarefaction that travel through the plasma. Over time, these waves can merge into larger structures, producing regions of enhanced density, followed by thinner, more diffuse zones. The result is a highly structured but continuously shifting environment. As the solar wind expands further, it approaches a boundary where its outward velocity is no longer sufficient to push directly against the interstellar medium. At this point, the flow slows from supersonic speeds relative to the surrounding plasma to subsonic speeds. This transition does not occur abruptly, but through a broad deceleration region where energy is gradually redistributed. The kinetic energy of the solar wind is converted into heat magnetic turbulence and particle scattering. This slowing region is filled with heated plasma that has been compressed by the interaction with interstellar space. The temperature increases as the flow decelerates, not because energy is added, but because directed motion is transformed into random particle motion. In this region, magnetic fields become highly distorted, forming tangled structures that influence the trajectories of charged particles. These fields act as channels and barriers, guiding plasma flow in complex patterns that vary over time. Neutral atoms from the interstellar medium continue to drift into this region. Unlike charged particles, they are not immediately affected by magnetic fields, and can travel relatively freely across boundaries. However, as they encounter solar radiation or collide with energized solar wind particles, they may lose or gain electrons. Once ionized, they become part of the plasma system and are carried along by magnetic forces. This continuous exchange creates a mixing layer between solar and interstellar material. The interaction between solar wind and interstellar medium also produces energetic particles through processes of acceleration. When plasma flows collide or compress, they can generate shock fronts that energize particles to higher speeds. These particles can then move independently of the surrounding flow, forming populations of energetic ions and electrons that spread throughout the outer heliospheric region. Their presence contributes to the overall pressure balance in this zone. Magnetic turbulence in this region is particularly significant. As large-scale magnetic fields are stretched and compressed, they break into smaller fluctuating structures. These fluctuations create regions where particle motion becomes chaotic, with trajectories constantly changing direction. Despite this complexity, the overall system remains governed by conservation of energy and momentum, ensuring that large-scale flow patterns persist even as local behavior becomes unpredictable. The outer solar wind region also reflects the history of solar activity over long timescales. Because particles take years to travel from the Sun to this distance, the structure of the plasma contains a record of past solar conditions. Variations in solar output are carried outward like ripples in a vast medium, gradually shaping the outer heliosphere. In this way, the region acts as a delayed reflection of the Sun's changing behavior. As the solar wind continues to slow, it approaches a transition zone where the influence of the interstellar medium becomes increasingly dominant. Here, the outward pressure of solar particles is balanced by the inward pressure of galactic gas and magnetic fields. The interaction between these two forces creates a boundary region that is neither fully solar nor fully interstellar. Instead, it exists as a mixed environment where properties of both regions coexist. This transition is characterized by strong gradients in density, temperature, and magnetic structure. Plasma flows become highly irregular, and particle trajectories are frequently altered by collisions and field variations. The environment is no longer dominated by smooth outward expansion, but by complex feedback between opposing pressures. Energy is redistributed continuously across scales from large flows down to microscopic particle interactions. Even in this distant region, the Sun's influence remains detectable. The solar wind does not simply end, but gradually fades into interstellar space through a series of transformations. Its particles, fields, and energy continue to interact with the surrounding medium, shaping a broad and dynamic boundary between star and galaxy. This boundary is not fixed, but constantly evolving as both solar output and interstellar conditions change over time. Beyond the outermost slowing region of the solar wind lies a broad transitional environment where solar influence and interstellar pressure reach a near balance. In this zone, the flow of solar plasma is no longer freely expanding outward, yet it has not fully merged with the surrounding galactic medium. Instead, it forms a complex interface shaped by compression, deflection, and gradual mixing. This region is not a sharp boundary, but a wide evolving layer in which physical conditions shift continuously over large distances. As the solar wind approaches this interface, it is forced to slow further and compress against the incoming interstellar flow. The plasma becomes denser and hotter due to the conversion of directed motion into random thermal motion. Particles that once moved outward in a relatively uniform stream now experience frequent collisions and magnetic disturbances. These interactions increase turbulence, breaking the flow into irregular structures that vary in size and intensity. Magnetic fields play a central role in shaping this region. The solar magnetic field carried outward by the solar wind becomes distorted as it meets the interstellar magnetic field. These two systems do not simply cancel or merge, but instead interact through twisting, reconnection, and realignment. Magnetic reconnection occurs when field lines break and reconnect in new configurations, releasing stored magnetic energy into particle motion and heat. This process contributes to localized heating and particle acceleration throughout the interface. Within this turbulent zone, charged particles follow complex paths determined by both solar and interstellar magnetic influences. Their motion is no longer dominated by a single outward direction, but by competing forces that redirect them repeatedly. Some particles are deflected back toward the inner heliosphere, while others are pushed outward into interstellar space. This exchange creates a dynamic circulation pattern, where material and energy are continuously redistributed. Neutral atoms from interstellar space continue to enter this region without direct magnetic influence. These atoms move in straight paths until they encounter ionizing processes such as ultraviolet radiation from the Sun or collisions with energetic particles. Once ionized, they become part of the plasma environment and are entrained in the magnetic structure of the region. This process gradually blends solar and interstellar material, creating a partially mixed boundary layer. The density of particles in this interface remains low in absolute terms, yet it is significantly higher than in the surrounding interstellar medium. This increase in density results from compression of solar wind plasma as it slows and accumulates near the boundary. The temperature is also elevated, reflecting the energy converted from bulk flow into particle motion. Despite these changes, the environment remains far more diffuse than any planetary atmosphere. Turbulence in this region is not random in the strict sense, but follows statistical patterns governed by plasma physics. large-scale flows break down into smaller eddies, and fluctuations transferring energy across different scales. This cascade of energy continues until it reaches the level of individual particle motion, where it is dissipated as heat. The result is a multi-scale structure where order and disorder coexist within the same physical framework. Cosmic rays, high-energy particles originating from distant astrophysical sources, interact with this region in complex ways. As they travel through the boundary layer, their trajectories are influenced by magnetic fields and plasma density variations. Some are scattered, some lose energy, and others pass through with little change. The heliospheric interface therefore acts as a partial filter, modifying the intensity and composition of cosmic radiation that enters the inner solar system. The shape of this interface is not uniform around the Sun. It varies depending on the direction of motion of the solar system through the galaxy and the local properties of the interstellar medium. In some directions the boundary extends farther outward, while in others it is compressed more tightly. This asymmetry produces a distorted, elongated structure rather than a symmetrical shell. The geometry changes slowly over time as external conditions evolve. Energy exchange across this region occurs continuously. Solar wind particles transfer momentum to interstellar atoms, while incoming interstellar particles deposit energy into the outer heliospheric plasma. Magnetic interactions further contribute to this exchange, converting field energy into particle motion and vice versa. This constant redistribution of energy ensures that the interface remains active and dynamic rather than static. Although this region marks a transition between two major cosmic environments, it does not represent a final boundary. Instead, it functions as a broad zone of interaction, where the identity of particles and fields becomes gradually shared between solar and galactic systems. Over time, the material passing through this region may be altered in state, direction, and energy, but it continues its journey through a larger cosmic continuum. The interface ultimately connects the solar system to the wider galaxy, allowing matter and energy to flow between scales. It represents a threshold where local stellar influence begins to yield to the broader structure of the Milky Way, yet still retains enough solar imprint to remain distinct. This balance defines the nature of the region and prepares the gradual transition into deeper interstellar space. Beyond the heliospheric interface, the environment transitions more fully into interstellar space, where the influence of the Sun becomes increasingly indirect. In this region, the plasma that once originated from the solar wind is now highly dispersed, and the dominant conditions are set by the broader interstellar medium. The remaining solar particles are no longer organized into a coherent outward flow, but are instead mixed with galactic gas magnetic fields and energetic particles that have accumulated over long periods of cosmic activity. The density of matter here is extremely low, consisting primarily of hydrogen atoms and a smaller fraction of helium atoms. These atoms exist in a neutral state, or are weakly ionized depending on local radiation fields. The motion of particles is governed by a combination of gravitational influence from the Milky Way residual magnetic fields and random kinetic motion inherited from past energetic events such as supernovae. Over large distances, this creates a medium that is diffuse, yet structurally complex. Temperature in this region varies depending on the balance between heating and cooling processes. Ultraviolet radiation from nearby stars can ionize gas and increase thermal energy, while regions shielded from radiation allow atoms to cool and recombine into neutral form. This produces a patchwork of thermal environments ranging from warm ionized regions to cold neutral clouds. Each of these phases coexists within the same general interstellar space, forming a multi-phase medium. Magnetic fields continue to play an important role even far from the Sun. These fields are weak but extended, stretching across vast regions of space and influencing the motion of charged particles. Because the plasma is so diffuse, even small magnetic forces can significantly alter particle trajectories over long timescales. Charged particles spiral along field lines while neutral atoms move more freely until they encounter ionizing processes or collisions. Within this interstellar region, remnants of the heliosphere are gradually indistinguishable from the surrounding medium. Solar origin particles have been redistributed through diffusion and interaction, losing their original directional structure. Over time, the identity of these particles as part of a solar-driven flow disappears, and they become part of the general galactic environment. This blending illustrates the continuous exchange of matter between stellar systems and the galaxy as a whole. Cosmic rays become more prominent in this region. These high-energy particles originating from distant supernova explosions and other energetic astrophysical sources travel through interstellar space at nearly relativistic speeds. As they move, they interact with magnetic fields and occasionally with interstellar gas, producing secondary particles and contributing to ionization. Their presence helps maintain a low level of ionization even in regions that would otherwise be largely neutral. Dust grains are also present throughout this environment. These microscopic solid particles absorb and scatter starlight, affecting the propagation of electromagnetic radiation across space. Dust is formed in the outer layers of stars and in the remnants of supernova explosions, then dispersed into interstellar space, where it participates in chemical reactions. Over time, dust grains can accumulate ice mantles or organic compounds depending on local conditions, and serve as sites for molecular formation. In some regions, interstellar gas becomes concentrated into clouds. These clouds are not sharply defined, but exist as regions of higher density within the surrounding medium. They may be cold and neutral, with temperatures low enough to allow simple molecules such as molecular hydrogen to form. These clouds move slowly through space, shaped by gravity turbulence and magnetic forces. Their internal structure is often complex, with regions of varying density and temperature. The interstellar medium is not static, but continuously evolving. Shock waves from distant stellar explosions propagate through it, compressing gas and triggering new patterns of motion. These shocks can heat gas, ionize atoms, and redistribute matter over large scales. Over long time scales, such processes contribute to the cycling of material between stars and the interstellar environment, forming a dynamic galactic ecosystem. In this region, the Sun's past influence is no longer directly visible as a structured flow, but it still exists in the distribution of particles and in subtle variations in plasma properties. These remnants are gradually erased as interstellar processes dominate. The transition from heliospheric dominance to galactic equilibrium is therefore not abrupt, but represents a long fading of solar imprint into the background of the Milky Way. Energy in this region is distributed through radiation particle motion and magnetic interactions. There is no single dominant source, but rather a balance of contributions from many distant stars and past energetic events. This creates a stable yet dynamic environment in which matter is constantly reshaped on timescales far longer than human experience. The interstellar medium ultimately serves as the broader context in which all stellar systems exist. It is the material reservoir from which new stars form and into which old stellar remnants disperse. In this sense, the region beyond the heliosphere is not empty space, but a continuous medium that connects all parts of the galaxy through subtle but persistent physical processes. Farther within the interstellar environment, the structure of space becomes more clearly defined by large-scale variations in density and temperature, rather than any influence from a single nearby star. In this region, gas and dust are arranged into broad, uneven distributions that reflect the long history of stellar activity in the Milky Way. The material is still extremely diffuse compared to planetary standards, yet it forms coherent patterns over distances spanning many light years. These patterns emerge from the interplay of gravity turbulence, magnetic fields, and radiation pressure. Hydrogen remains the dominant element, existing mostly in neutral atomic form. In some areas it is slightly ionized by ultraviolet radiation from distant stars or by residual energetic particles. The balance between ionized and neutral hydrogen determines many of the physical properties of the region, including how it responds to magnetic fields and how it interacts with radiation. Helium is also present, though less reactive and less influential in shaping large-scale structures. Together, these simple elements form the foundation of the interstellar medium. Temperature differences define much of the internal structure of this region. Cold clouds can reach temperatures only a few tens of degrees above absolute zero, allowing atoms to move very slowly and enabling the formation of simple molecules. In contrast, warmer regions can reach thousands of degrees where gas becomes partially ionized and more responsive to electromagnetic forces. These temperature variations exist side by side, often separated by gradual transitions rather than sharp boundaries. Magnetic fields thread through the interstellar medium in broad, gently curved lines. These fields are not strong in absolute terms, but because the density of matter is so low, their influence becomes significant. Charged particles follow spiral paths along these magnetic lines, while neutral particles move more freely until they become ionized. Over time, this interaction between gas motion and magnetic structure helps shape filament sheets and cloud-like formations. Turbulence plays a central role in maintaining the complexity of this environment. Energy injected by distant supernova explosions or stellar winds cascades through the gas, breaking large structures into smaller, more intricate patterns. This turbulence does not dissipate quickly because the medium is so thin. Instead, it persists over long periods, continually reshaping the distribution of matter. The result is a dynamic equilibrium where structure is constantly formed and dispersed. Dust grains continue to influence the interstellar medium at this scale. These small solid particles absorb ultraviolet and visible light, altering the way distant stars are observed from within or beyond these regions. Dust also provides surfaces for chemical reactions, allowing simple molecules to form even in extremely cold environments. Over time, these grains can grow icy layers composed of water, carbon monoxide, and other simple compounds depending on local conditions. In denser parts of this region, molecular clouds begin to form. These clouds are composed primarily of molecular hydrogen, where two hydrogen atoms are bonded together. Molecular hydrogen is difficult to observe directly, but its presence is inferred through associated tracer molecules and emission patterns. These clouds are the coldest and densest structures in the interstellar medium, though still far more diffuse than any atmosphere familiar on planetary scales. Within molecular clouds, gravity slowly begins to play a more noticeable role. Although thermal pressure and magnetic support often counteract collapse, small fluctuations in density can grow over time. These fluctuations may eventually lead to regions where material begins to contract under its own gravity, setting the initial conditions for future star formation. However, this process is extremely slow, unfolding over millions of years. Cosmic rays continue to permeate this environment, providing a constant source of ionization. Even in the densest clouds, they penetrate deeply enough to influence chemistry and maintain a low level of electrical activity. This ionization is important for coupling the gas to magnetic fields, ensuring that even neutral regions remain partially connected to the broader electromagnetic structure of the galaxy. The interstellar medium at this stage is no longer a simple diffuse background, but a structured and evolving system. It contains regions of relative calm and regions of active change, all linked through the continuous flow of energy and matter. The Sun, far from being a central influence here, is only one of many stars contributing to the ongoing cycle of material in the galaxy. Over long timescales, material in this region may be incorporated into new stellar systems or redistributed by energetic events. The interstellar medium therefore acts as both a repository and a source storing matter between generations of stars and providing the raw ingredients for future cosmic structures. In this way, it forms an essential part of the galactic ecosystem, connecting past, present, and future states of stellar evolution. Deeper within the interstellar medium, the structure of gas becomes increasingly organized into large, coherent formations shaped by long-term galactic processes. These formations are not static objects, but evolving regions where gravity pressure, magnetic fields, and radiation continuously interact. The matter here remains extremely diffuse compared to planetary atmospheres, yet it is sufficiently structured to reveal patterns that extend across hundreds of light years. In this environment, neutral hydrogen continues to dominate the composition of space. It exists in vast clouds that drift slowly through the galaxy, sometimes accumulating into larger complexes. These clouds are not solid or sharply bounded, but instead fade gradually into surrounding space. Their edges are defined by subtle changes in density and temperature, rather than distinct physical barriers. Within them, hydrogen atoms move slowly, occasionally colliding and exchanging energy. As conditions vary across these clouds, some regions become colder and denser than others. In the coldest zones, temperatures drop to levels where thermal motion is extremely limited. Here, atoms can approach one another closely enough for weak electromagnetic interactions to become significant. Over time, these conditions allow the formation of simple molecules, particularly molecular hydrogen, which becomes the dominant form of hydrogen in these colder regions. The transition from atomic hydrogen to molecular hydrogen marks an important change in the physical behavior of the gas. Molecular regions respond differently to radiation, and magnetic fields often becoming more shielded and less ionized. This shielding effect allows the interior of dense clouds to remain cold and stable, even when surrounded by more energetic interstellar environments. As a result, molecular clouds can persist for long periods without dispersing. Magnetic fields continue to influence the structure of these clouds. Although weak, they are capable of guiding the motion of charged particles and subtly shaping the overall geometry of the gas. Filament-like structures often emerge aligned along magnetic field lines or shaped by turbulent flows. These filaments can stretch across vast distances, forming interconnected networks of dense material within the larger cloud system. Turbulence remains a persistent feature at this scale. Energy injected by distant supernova remnants or stellar winds propagates through the interstellar medium, creating waves of compression and rarefaction. These waves interact with existing structures, amplifying some regions of density while dispersing others. Over time, this leads to a constantly shifting landscape of gas and dust, where no structure remains permanent. Dust grains continue to play a subtle but important role in shaping these environments. They absorb ultraviolet radiation, helping to protect molecular hydrogen from being broken apart by energetic photons. In addition, dust surfaces act as catalysts for chemical reactions, allowing atoms to combine into more complex molecules. These processes occur slowly but steadily, contributing to the chemical richness of the interstellar medium. Within denser regions of molecular clouds, gravity begins to exert a stronger influence. While still countered by internal pressure and magnetic support, gravity can gradually pull material inward in localized areas. These regions of slightly higher density can grow over time, becoming the seeds of future collapse. However, this process remains delicate, with many fluctuations dissipating before significant contraction occurs. Cosmic rays penetrate these clouds, maintaining a low level of ionization, even in regions shielded from starlight. This ionization is important for maintaining coupling between the gas and magnetic fields, ensuring that magnetic forces remain relevant even in cold, dense environments. Without this effect, the internal dynamics of molecular clouds would behave differently, potentially altering the balance between stability and collapse. The interstellar medium at this stage becomes a complex interplay of phases. Cold molecular regions exist alongside warmer atomic gas, all embedded within a larger, more diffuse environment. These phases exchange material and energy through slow diffusion shock waves and radiation. Over time, material cycles between these states, contributing to the long-term evolution of the galaxy. Although the Sun's direct influence is no longer present, its history remains embedded in the broader galactic context. The same processes that shape distant molecular clouds also shape the environment from which the solar system originally formed. In this way, the interstellar medium represents both the present condition of the galaxy and the ancestral material of stellar systems. The continuous movement of gas and dust through these regions ensures that the galaxy remains dynamic over astronomical timescales. Material is neither created nor destroyed in isolation, but constantly redistributed between stars and interstellar space. This ongoing cycle maintains the structure of the Milky Way and supports the formation of new generations of stars and planetary systems. Within the deeper molecular regions of interstellar space, the environment becomes increasingly structured by cold, dense accumulations of gas and dust. These regions, known as molecular clouds, represent some of the most chemically active yet physically calm areas of the galaxy. Despite their vast size, they remain extremely diffuse compared to any atmosphere, yet their internal balance of forces allows them to persist for millions of years without immediate collapse or dispersal. The primary component of these clouds is molecular hydrogen, formed when two hydrogen atoms bind together under cold shielded conditions. This molecule becomes stable in environments where ultraviolet radiation is largely blocked by surrounding dust. As a result, the interior of these clouds remains protected from energetic radiation, allowing temperatures to drop significantly. In these cold conditions, thermal motion slows and particles interact more gently, creating an environment where subtle forces become important. Dust grains are essential to this protective structure. These tiny solid particles absorb and scatter incoming ultraviolet and visible radiation, preventing it from penetrating deep into the cloud. The same grains also provide surfaces where chemical reactions occur. Atoms that land on dust surfaces can meet and bond, forming molecules that would be difficult to create in the gas phase alone. Over time, this leads to the formation of simple compounds, such as water, carbon monoxide, and ammonia, depending on local conditions. Inside molecular clouds, density is not uniform. Instead, it varies across a wide range of scales, forming clumps, filaments, and cores. These structures arise from the combined effects of turbulence, gravity, and magnetic fields. Turbulent motion continuously stirs the gas-creating regions of compression and rarefaction. Where compression is strong enough, material becomes locally denser, forming potential sites for further evolution. Magnetic fields thread through these clouds in subtle but persistent ways. Although weak in absolute strength, they influence the motion of charged particles and help shape the geometry of the gas. Filamentary structures often align along magnetic field lines, suggesting a close relationship between field orientation and cloud morphology. The fields also provide partial support against gravitational collapse, slowing the inward motion of material in many regions. gravity operates more effectively in the densest parts of the cloud. In these regions known as dense cores, the balance between thermal pressure turbulence and magnetic support becomes increasingly delicate. If a region becomes sufficiently dense, gravity can begin to dominate locally, initiating a slow contraction process. This contraction does not occur uniformly, but develops gradually influenced by surrounding conditions and internal variations. Cosmic rays continue to penetrate even the deepest parts of molecular clouds. These high-energy particles maintain a low level of ionization, which is essential for coupling the gas to magnetic fields. Without this ionization, the gas would behave more independently of magnetic structure. Instead, even neutral material retains a weak connection to the broader electromagnetic environment of the galaxy. As material slowly contracts within dense cores, energy begins to accumulate. Gravitational potential energy is gradually converted into heat, though this heat is often efficiently radiated away by molecular emissions. As a result, the collapse can proceed in a relatively cool environment, allowing the core to remain stable in a slow, controlled contraction phase over extended timescales. The internal structure of molecular clouds is constantly reshaped by external influences. Shockwaves from distant supernovae or stellar winds can compress regions of the cloud, triggering new patterns of density enhancement. These disturbances propagate through the cloud, interacting with existing structures, and sometimes reinforcing regions of collapse while dispersing others. Despite this activity, molecular clouds remain long-lived structures within the galaxy. Their evolution is governed by a balance between opposing forces, with no single process dominating completely. Over time, material cycles through different states, gradually shifting between diffuse gas-dense clumps, and eventually, in some cases, gravitationally bound cores that may lead to star formation. The Sun's formation history is connected to processes occurring in environments like these molecular clouds. Long before the solar system existed, similar regions of cold, dense gas provided the conditions necessary for the birth of stars and planetary systems. The interstellar medium therefore acts as both a current environment and a historical record of stellar origins. As molecular clouds evolve, they contribute to the ongoing cycle of matter within the galaxy. Material is continuously recycled between stars and interstellar space, ensuring that the galaxy remains chemically and structurally dynamic. This cycle operates over immense timescales, shaping the conditions under which new stars eventually emerge. Within the densest regions of molecular clouds, gravity begins to take a more decisive role, as local concentrations of gas reach thresholds where internal support mechanisms become less effective. These regions, often referred to as dense cores, represent the quiet beginning of long processes that may eventually lead to the formation of new stars. Even here, the material remains extremely diffuse compared to any planetary atmosphere, yet the balance of forces has shifted enough that contraction becomes increasingly likely over time. In these dense cores, hydrogen molecules dominate the composition of matter. The temperature remains very low, allowing thermal motion to stay minimal. This low-energy environment means that particles move slowly enough for gravity to gradually influence their distribution. As small irregularities in density develop, they can begin to grow, drawing more material inward and slowly increasing the contrast between dense and less dense regions. Dust grains continue to play a stabilizing and chemically active role. They absorb radiation from the surrounding interstellar field, keeping the interior of these cores shielded from external heating. At the same time, they facilitate chemical reactions on their surfaces, enabling the formation of molecules that would otherwise be difficult to produce in the gas phase. These processes contribute to a chemically rich but thermally cold environment. Magnetic fields thread through dense cores and influence the motion of charged particles. Even though most of the gas is neutral, The small fraction of ionized particles ensures that magnetic forces remain connected to the overall dynamics of the system. These fields can provide partial support against gravitational collapse, slowing the rate at which material contracts. The interplay between gravity and magnetic support creates a delicate balance that evolves slowly over time. Turbulence within dense cores is weaker than in more diffuse regions, but still present. It introduces small fluctuations in density and velocity, which can either enhance or counteract gravitational contraction. In some areas, turbulent compression helps initiate collapse by increasing local density, while in others it disperses material and delays further contraction. This dual role makes turbulence an important regulator of structure formation within molecular clouds. Cosmic rays penetrate deep into these regions, maintaining a minimal level of ionization. This ionization is crucial for enabling magnetic fields to influence the gas. Without it, the coupling between matter and magnetic structure would weaken significantly. Even in these shielded environments, therefore, the broader galactic environment continues to exert subtle but persistent influence. As dense cores evolve, they may begin to flatten or elongate under the combined effects of rotation and magnetic alignment. Even slight initial rotation can become more noticeable as contraction proceeds, leading to changes in shape and internal flow patterns. These rotational effects do not yet produce stars but represent early structural organization within collapsing material. The energy balance within these regions remains tightly regulated. As gravity pulls material inward, compressional heating increases, but much of this energy is radiated away through molecular emission processes. This radiative cooling allows contraction to continue without rapidly increasing internal pressure. The result is a slow and controlled evolution rather than a sudden collapse. Over long periods, some dense cores reach a point where gravitational forces begin to dominate over all opposing influences. At this stage, the material enters a more active phase of contraction, though it still remains deeply embedded within the parent molecular cloud. External pressure from surrounding gas helps confine the core, maintaining a stable boundary, while internal changes proceed. The interstellar medium surrounding these cores remains dynamic. Flows of gas and shock waves from distant astrophysical events continue to pass through the cloud, occasionally compressing or disturbing regions of relative stability. These interactions can either accelerate or inhibit collapse depending on their timing and direction. Although the Sun has already formed long ago, the same physical processes that operate in these dense cores were once responsible for its origin. The gradual accumulation of matter, the interplay of gravity, magnetic fields, and turbulence, and the slow cooling of contracting gas all contributed to the formation of the solar system. In this sense, dense cores represent the early conditions of stellar birth throughout the galaxy. As these regions evolve, they contribute to the continuous recycling of matter in the Milky Way. Material that once existed as diffuse interstellar gas becomes concentrated, potentially forming new stars which will later return material back into space through stellar winds and eventual stellar death. This cycle ensures that the galaxy remains in a constant state of transformation over vast timescales. As dense cores within molecular clouds continue to evolve, the internal balance of forces shifts further toward gravitational dominance in certain regions. The material, still composed primarily of molecular hydrogen and dust, becomes increasingly concentrated toward the center of these cores. The surrounding cloud continues to provide external pressure, but inside the most compact regions, gravity gradually reshapes the structure of the gas into a more centrally focused distribution. At this stage, the core is no longer uniform. A clear gradient forms with higher density near the center and progressively lower density toward the outer layers. This gradient develops slowly as particles drift inward under gravity, while still interacting through collisions and radiation processes. the motion remains gentle on large scales, yet the cumulative effect over long periods leads to significant structural change. Dust grains within the core continue to regulate temperature by absorbing and re-emitting radiation. Because the environment is heavily shielded from external starlight, the primary sources of energy are internal compression and weak background radiation. The dust allows the core to radiate away excess energy, efficiently preventing rapid heating. This cooling process is essential for maintaining conditions where gravitational contraction can continue. Magnetic fields remain present, threading through the gas and influencing the motion of charged particles. Even though ionization levels are low, they are sufficient to keep the gas partially coupled to the magnetic structure. In some regions, magnetic pressure resists collapse, slowing the inward flow of material. In others, matter flows more freely along field lines, creating elongated shapes that reflect the direction of the magnetic field. Turbulence continues to act as a regulating force. Small-scale chaotic motions introduce variations in density and velocity, which can either enhance or disrupt contraction depending on local conditions. As the core becomes denser, turbulence tends to decay, but it does not disappear entirely. Instead, it becomes more localized, influencing the fine structure of the collapsing region. Cosmic rays remain one of the few external energetic influences penetrating deep into the core. Their interactions with the gas maintain a minimal level of ionization, which in turn preserves the connection between matter and magnetic fields. This weak but persistent coupling ensures that magnetic forces remain relevant even in the densest regions of the cloud. As contraction progresses, the central region of the core begins to differentiate from its surroundings. The density increases more rapidly near the center, and the gravitational potential well deepens. Material from outer regions gradually flows inward, feeding this central accumulation. The process remains slow in absolute terms, unfolding over long time scales, but it represents a clear transition from diffuse cloud structure toward a more concentrated object. Energy released by gravitational contraction is largely converted into thermal motion, but efficient radiative cooling prevents this heat from accumulating quickly. Molecular emissions, particularly from hydrogen and other trace molecules, carry energy away from the system. This balance between heating and cooling allows the core to remain stable, even as it slowly evolves toward higher density states. The surrounding molecular cloud continues to interact with the core through pressure and material exchange. External shocks from distant stellar events may compress the cloud, influencing the rate of contraction. In some cases, such disturbances can accelerate collapse by increasing local density, while in others they can disperse material and temporarily stabilize the structure. Rotation becomes more significant as contraction continues. Even a small initial angular momentum is amplified as the core shrinks, leading to an increase in rotational speed. This rotation begins to influence the geometry of the collapsing material, encouraging flattening and the development of disc-like structures. These changes remain gradual but increasingly important in shaping the later evolution of the system. Although still far from forming a star, the core now represents a distinct stage in the life cycle of interstellar matter. It is no longer simply part of a diffuse cloud, but a concentrated region undergoing organized inward motion under gravity. This transition reflects the broader cycle of matter in the galaxy, where diffuse gas gradually becomes structured, condensed, and eventually transformed into stellar objects. The processes occurring here are not isolated, but part of a continuous galactic system. Material that has drifted through interstellar space for millions of years now becomes part of a focused gravitational structure. In time, similar regions across the galaxy will follow comparable paths, ensuring that the cycle of star formation remains ongoing and widespread. As the collapsing core continues its slow inward motion, the central region becomes increasingly distinct from its surroundings. The density rises steadily, and the material near the center begins to behave as a tightly bound structure influenced primarily by gravity. The outer layers still respond to turbulence, magnetic fields, and external pressure from the molecular cloud, but the inner region gradually decouples from these larger-scale influences. In this deeper stage of contraction, molecular hydrogen remains the dominant component, but its role begins to change as density increases. Collisions between particles become more frequent, and energy transfer through these interactions becomes more efficient. The gas remains cold in an absolute sense compared to stellar interiors, yet it is slowly warming due to gravitational compression. This increase in internal energy is moderated by radiation, which continues to carry heat away from the system. Dust grains embedded within the collapsing material play a continuing role in regulating both temperature and chemistry. They absorb radiation and re-emit it at longer wavelengths, allowing the core to remain relatively cool even as compression increases. On their surfaces, simple molecules continue to form and interact, contributing to a chemically active but thermally controlled environment. Magnetic fields remain threaded through the core, influencing the motion of charged particles. As density increases, the coupling between matter and magnetic fields becomes more complex. In some regions, magnetic forces help guide the collapse along preferred directions, leading to anisotropic structures. In others, gravitational forces dominate more strongly, allowing matter to flow inward with less resistance from magnetic support. Turbulence within the core becomes increasingly localized. Large-scale chaotic motion diminishes as the structure contracts, but smaller-scale fluctuations persist. These fluctuations can create localized pockets of enhanced density or temporarily resist inward motion. Over time, however, gravity smooths out many of these irregularities, drawing material toward the center in a more coherent flow. Cosmic rays continue to provide a steady background of ionization. Even in the densest regions, they penetrate deeply enough to maintain a weak coupling between gas and magnetic fields. This coupling ensures that magnetic influence does not vanish entirely, even as the material becomes more concentrated. The persistence of this effect helps regulate the collapse process, preventing it from becoming entirely unstructured. As the central region grows denser, it begins to form a distinct gravitational center. Material from the surrounding envelope flows inward, feeding this central accumulation. The gravitational potential becomes deeper, meaning that particles require increasingly more energy to escape the region. This deepening well marks a transition toward a more self-contained structure within the broader cloud. Thermal energy generated by compression increases, but radiative cooling remains efficient. Molecules within the gas emit radiation at infrared wavelengths, allowing energy to escape into surrounding space. This balance between heating and cooling maintains a relatively stable temperature profile despite ongoing contraction. The core therefore evolves slowly rather than undergoing rapid collapse. The surrounding molecular cloud continues to influence the system through external pressure and occasional shock waves. These disturbances originating from distant stellar events can compress the core further or disturb its internal balance. Depending on their strength and timing, they may accelerate the collapse or temporarily disrupt it. However, the overall trend toward increasing central density remains dominant. Rotation becomes increasingly important in shaping the structure of the collapsing material. As the core contracts, conservation of angular momentum causes rotational speed to increase. This leads to the gradual flattening of the inner region, forming a structure that is no longer purely spherical. Instead, the material begins to arrange itself into a flattened, rotating configuration that reflects its initial angular momentum. This rotational flattening is an important step in the evolution of interstellar matter. It introduces directional structure into what was once a relatively isotropic cloud. As the system evolves further, This structure will play a critical role in organizing material into more complex forms. For now, it remains a subtle but growing influence on the dynamics of the collapsing core. Although still deeply embedded within the molecular cloud, the core now represents a clearly defined stage of gravitational evolution. It is no longer simply a passive part of the interstellar medium, but an active site of structured inward motion. The processes occurring here are part of a broader galactic cycle, in which diffuse gas is gradually transformed into concentrated objects under the influence of gravity-magnetic fields and radiation processes. As the collapsing core continues to contract, the inner region becomes increasingly dominated by gravity, while the outer envelope still reflects the influence of the surrounding molecular cloud. The contrast between these two zones grows more pronounced over time. The central material becomes denser and more compact, while the outer layers remain more diffuse and responsive to external turbulence and pressure variations. This internal separation marks a deeper stage in the evolution of interstellar matter. Within the central region, molecular hydrogen remains abundant, but the environment becomes progressively less stable for simple molecular structures. Frequent collisions between particles increase the rate of energy exchange, and the gas responds more directly to compressional forces. Although the temperature is still relatively low compared to stellar interiors, it rises gradually as gravitational energy is converted into heat. This energy is not retained indefinitely as radiation continues to carry it away into surrounding space. Dust grains embedded in the collapsing structure continue to influence both thermal balance and chemical processes. They absorb radiation from the dense interior and re-emit it in infrared wavelengths, helping regulate temperature. Their surfaces provide sites for chemical reactions, though the increasing density and motion of gas begin to alter how frequently particles interact with these grains. Over time, the role of dust shifts from passive absorber to active participant in the evolving thermal environment. Magnetic fields remain interwoven with the collapsing material, although their influence becomes increasingly complex as density rises. In some regions, magnetic pressure resists further contraction, slowing the inward flow of matter. In other regions, material is guided along field lines, allowing collapse to proceed more efficiently in certain directions. This anisotropic behavior contributes to the gradual development of structured geometry within the core. Turbulence, while reduced on large scales, continues to operate at smaller scales within the dense gas. These residual motions introduce irregularities in density and velocity, which can either support or locally enhance collapse. Over time, however, gravitational forces tend to dominate these fluctuations, smoothing out the structure and drawing material toward the central region. The interplay between turbulence and gravity remains a key factor in determining the fine structure of the collapsing core. Cosmic rays persist as one of the few external energetic influences capable of penetrating the dense interior. Their interactions with the gas maintain a low level of ionization, which ensures that magnetic fields remain partially coupled to the matter. This coupling is essential for preserving the influence of magnetism in an environment that is otherwise dominated by neutral particles. Even in these dense conditions, the broader galactic environment continues to exert subtle control. As contraction proceeds, the central region becomes increasingly compact and gravitationally dominant. Material from the surrounding envelope continues to flow inward, feeding this growing core. The gravitational potential deepens, making it progressively more difficult for particles to escape once they enter the central region. This growing concentration of mass marks a transition toward a more defined central object within the cloud. Energy produced by gravitational compression is still efficiently radiated away primarily through molecular emission in infrared wavelengths. This radiative cooling prevents rapid temperature increases and allows contraction to proceed in a controlled manner. Without this cooling mechanism, internal pressure would rise more quickly, and potentially halt or slow the collapse. Instead, the balance between heating and radiation maintains a steady inward evolution. The surrounding molecular cloud continues to influence the collapsing core through both pressure and dynamic interactions. Shock waves traveling through the cloud can compress or disturb the core, altering its rate of contraction. These external influences introduce variability into the collapse process, but they do not fundamentally change its overall direction toward increasing central density. Rotation plays an increasingly important role in shaping the geometry of the collapsing material. As angular momentum is conserved, the rotation rate increases, leading to stronger centrifugal effects in the inner regions. This causes the material to flatten further, gradually forming a more disc-like structure around the central concentration. This flattening is a natural consequence of the interplay between gravity and rotation. The formation of this flattened structure introduces a new level of organization within the collapsing core. Material is no longer moving purely inward, but begins to follow rotationally influenced paths, creating a more complex internal flow pattern. This marks a significant transition in the structural evolution of the system, setting the stage for later stages of star formation. Although still deeply embedded within the molecular cloud, the core now exhibits clear signs of organized gravitational collapse. It has moved beyond the diffuse interstellar state and into a structured evolving system where multiple physical processes interact in a coordinated manner. This stage represents one of the essential pathways through which interstellar matter transitions into stellar objects. As the collapsing core continues its inward evolution, the central region becomes increasingly compact and physically distinct from its surroundings. The density gradient between the inner core and outer envelope grows sharper, creating a structure where gravity dominates the center, while the outer layers remain influenced by residual turbulence, magnetic fields, and external pressure from the molecular cloud. This differentiation marks a clear progression in the transformation of diffuse interstellar gas into a more organized self-gravitating system. In the central region, molecular hydrogen remains the primary constituent, but its behavior is increasingly governed by frequent interactions between particles. Collisions become more efficient at redistributing energy, and the gas responds more directly to compressional forces. Although still cold relative to stellar interiors, the gradual increase in temperature reflects the continuous conversion of gravitational energy into internal motion. This process remains balanced by radiation, which carries energy away and prevents runaway heating. Dust grains continue to regulate the thermodynamic and chemical environment of the collapsing core. By absorbing radiation and re-emitting it in longer wavelengths, they maintain a cooling pathway that allows contraction to proceed steadily. The grains also influence the local chemistry by providing surfaces for molecular interactions. As density increases, their relative role becomes more complex, with both shielding and catalytic effects, shaping the evolving composition of the gas. Magnetic fields maintain a significant but increasingly intricate influence on the system. As the core contracts, field lines become compressed and distorted, creating regions of enhanced magnetic pressure and areas where matter flows more freely along field-aligned directions. This results in anisotropic collapse, where contraction is not uniform but shaped by the geometry of the magnetic field. The interplay between gravity and magnetism becomes more pronounced as the system becomes denser. Turbulence persists in a reduced but still meaningful form. Large-scale chaotic motions diminish as gravity organizes the flow inward, yet small-scale fluctuations remain embedded within the collapsing material. These fluctuations can momentarily enhance local density or create resistance to collapse, but over time they are smoothed by gravitational dominance. The residual turbulence contributes to fine structural variations within the core. Cosmic rays continue to penetrate the dense environment, providing a steady source of ionization. This ionization, though weak, is crucial for maintaining coupling between the gas and magnetic fields. Without it, magnetic forces would decouple from neutral matter, altering the dynamics of collapse. Instead, even in these shielded regions, the broader galactic environment retains a subtle but persistent influence on local structure. As material flows inward, the central region becomes increasingly self-contained. The gravitational potential deepens, and the ability of particles to escape diminishes significantly. This growing central concentration represents a transition from a diffuse cloud structure toward a more defined gravitational object. Surrounding material continues to feed this central region, reinforcing its growth and stability. Thermal energy generated by compression remains efficiently radiated away through molecular emission processes. Infrared radiation carries energy outward from the dense interior, allowing contraction to proceed without rapid increases in internal pressure. This balance between heating and cooling ensures that the collapse remains gradual and controlled, rather than explosive or abrupt. The surrounding molecular cloud continues to act as both reservoir and regulator. External shocks and pressure waves propagate through the cloud, occasionally compressing the core further or perturbing its internal structure. These interactions introduce variability into the collapse process, but the overall trend toward increasing central density remains dominant and uninterrupted. Rotation becomes increasingly significant in shaping the evolving structure. As angular momentum is conserved, the rotational velocity increases, leading to stronger centrifugal effects in the inner regions. This results in continued flattening of the collapsing material, reinforcing the formation of a disc-like structure around the central concentration. This rotational organization introduces a new geometric framework within the system. Within this flattened configuration, material flows along both radial and rotational paths, creating a complex internal structure. Matter is no longer simply moving inward, but is also redistributed along orbital trajectories shaped by the balance of gravity and rotation. This marks an important stage in the transition from diffuse cloud to organized prestellar structure. Although still embedded within the molecular cloud, the core now exhibits a clear internal hierarchy of forces and structures. Gravity dominates the center, magnetic fields shape the flow, turbulence introduces fine-scale variation, and radiation regulates temperature. Together, these processes define a dynamic but coherent system that continues evolving toward the formation of a new stellar object. As the collapsing core progresses further in its evolution, the central region becomes increasingly compact, and the surrounding structure organizes into a more defined and layered configuration. The contrast between the dense inner core and the extended outer envelope becomes more pronounced, reflecting the growing dominance of gravity in shaping the system. The material is no longer distributed in a relatively uniform cloud, but instead arranged into distinct zones governed by different physical processes operating simultaneously at different scales. In the innermost region, the gas is now highly compressed compared to earlier stages. Molecular hydrogen still dominates, but the frequency of collisions has increased significantly, allowing energy to be redistributed rapidly across small volumes. This leads to a gradual rise in temperature as gravitational energy is continuously converted into internal motion. However, radiative processes remain efficient enough to prevent sudden thermal escalation, allowing the collapse to remain controlled and gradual. Dust grains continue to play an important role in moderating the environment. By absorbing energy from the surrounding gas and re-emitting it as infrared radiation, they provide a critical cooling mechanism that supports continued contraction. Their surfaces also remain active sites for chemical interactions, although the increasing density and energy of collisions begin to alter reaction pathways. Over time, the dust becomes embedded within a more tightly bound and dynamic medium. Magnetic fields compressed by the inward motion of gas become more structured and dynamically significant. The field lines are drawn inward and stretched, creating regions where magnetic pressure resists collapse, and other regions where material flows more freely along field-aligned directions. This leads to a highly anisotropic structure in which the geometry of collapse is strongly influenced by magnetic orientation. The interaction between gravity and magnetism becomes increasingly complex at these higher densities. Turbulence continues to operate at reduced scales, but still contributes to the internal variability of the system. Large-scale chaotic motion has diminished, yet small-scale fluctuations persist and influence local density and velocity. These fluctuations can momentarily enhance collapse in some regions or introduce temporary resistance in others, but overall gravitational forces gradually smooth out irregularities, guiding the system toward greater central concentration. Cosmic rays remain a persistent external influence, penetrating deeply into the dense core and sustaining a low level of ionization. This ionization ensures continued coupling between the gas and magnetic fields, allowing magnetic forces to remain effective even in regions dominated by neutral matter. Without this ongoing interaction, the magnetic structure would decouple, significantly altering the dynamics of collapse. As the central region grows denser, it becomes increasingly gravitationally self-contained. The potential well deepens further, and material entering this region becomes more strongly bound. The flow of matter is now clearly directed inward, with outer layers steadily feeding the central accumulation. This process strengthens the distinction between the inner core and its surrounding envelope, marking a clear structural hierarchy within the collapsing system. Energy generated by contraction continues to be radiated away primarily through molecular emission in the infrared range. This radiative cooling remains essential for maintaining the balance that allows collapse to proceed. Without it rising, temperatures would increase pressure and slow or halt contraction. Instead, the system maintains a regulated inward evolution, supported by efficient energy loss mechanisms. The surrounding molecular cloud continues to influence the core through pressure shocks and material exchange. External disturbances propagate through the cloud and occasionally interact with the collapsing region, either enhancing or disrupting local density structures. Despite these interactions, the overall trajectory toward increasing central concentration remains stable and persistent. Rotation plays an increasingly defining role in shaping the structure of the collapsing material. As angular momentum is conserved during contraction, rotational velocity increases, leading to stronger centrifugal effects. This results in a more pronounced flattening of the inner structure, forming a clearer disc-like configuration around the central mass concentration. This disc represents a key stage in organizing material into a more ordered system. Within this rotating and flattened structure, matter follows increasingly organized trajectories, influenced by both gravitational and centrifugal forces. Material flows inward, while simultaneously orbiting the central region, creating a dynamic balance of motion. This dual movement reflects the transition from chaotic cloud dynamics to structured pre-stellar organization. At this stage, the core has become a highly structured evolving object embedded within the molecular cloud. It is no longer simply a region of enhanced density, but a complex system governed by interacting forces that operate across multiple scales. Gravity, magnetic fields, turbulence, radiation, and rotation all contribute to its behavior, guiding it toward the final stages of pre-stellar collapse. As the collapsing structure continues its inward progression, the central region approaches a state where density, pressure, and temperature increase steadily within a deeply gravitationally bound environment. The surrounding molecular cloud still exists as a broad reservoir of gas and dust, but its direct influence on the inner region becomes more limited as the core becomes increasingly self-contained. The system now exists as a tightly organized pre-stellar object embedded within a much larger interstellar structure. In the inner region, molecular hydrogen is still present, but its behavior reflects the intensifying conditions of compression. Collisions between particles occur, frequently redistributing energy across very small distances. The gas responds more directly to gravitational forces, and the gradual increase in temperature continues as contraction proceeds. Despite this warming trend, radiative cooling remains effective enough to carry away excess energy, allowing the inward evolution to continue without abrupt instability. Dust grains remain interwoven throughout the dense material, continuing to regulate thermal balance by absorbing and re-emitting radiation. Their presence ensures that energy generated by compression does not accumulate too rapidly within the core. In addition, the grains influence the chemical environment by providing surfaces for molecular interactions. Although the increasing density and energy of collisions gradually alter the efficiency and pathways of these processes, magnetic fields compressed and distorted by ongoing collapse maintain a structured but increasingly complex role in guiding the flow of matter. Field lines are drawn inward and reshaped by gravitational contraction, creating regions of both resistance and channeled flow. In some areas, magnetic pressure slows the inward motion of gas, while in others, material moves more freely along aligned structures. This results in a highly anisotropic configuration, where collapse proceeds unevenly across different directions. Turbulence persists at small scales, though it is significantly reduced compared to earlier phases. Residual chaotic motions continue to introduce variations in density and velocity, but gravitational forces increasingly dominate the overall structure. These fluctuations become less influential over time, gradually being incorporated into the larger coherent inward flow of material. Cosmic rays continue to penetrate the dense environment, maintaining a minimal level of ionization throughout the core. This weak ionization is essential for preserving the coupling between matter and magnetic fields. Even as the system becomes more compact and shielded from external radiation, the influence of distant energetic processes in the galaxy remains present through these high-energy particles. The central region has now become strongly gravitationally bound with a deepening potential well that governs the motion of all surrounding material. Gas flows steadily inward, feeding the central concentration and reinforcing its growth. The distinction between inner core and outer envelope is now well defined, with clear gradients in density, temperature, and motion. Energy released through continued contraction is still efficiently radiated away, primarily in infrared wavelengths. This radiative loss allows the collapse to remain stable and gradual, preventing excessive buildup of internal pressure. The balance between gravitational compression and energy emission continues to regulate the evolution of the system. The surrounding molecular cloud remains an active environment capable of influencing the core through pressure variations and shock interactions. However, these external influences now play a secondary role compared to the dominant inward pull of gravity within the core. The overall direction of evolution remains consistent toward increasing central density and structural organization. Rotation has now become a defining feature of the system's geometry. As angular momentum is conserved, the increasing rotational speed leads to a flattened disk-like structure surrounding the central concentration. Within this disk, material moves along combined radial and orbital paths, reflecting the balance between inward gravitational forces and outward centrifugal effects. This structure represents a key transitional stage in the evolution from cloud to star. The system now exists as a coherent, evolving prestellar object shaped by the interplay of gravity-magnetic fields, turbulence, radiation, and rotation. It represents the culmination of long interstellar processes that began in diffuse gas and progressed through successive stages of condensation and organization. Within this structure, matter is steadily reorganized into a form that will eventually give rise to a new stellar source, continuing the broader cycle of matter within the galaxy.